Consider this. A traveler from a distant star system disintegrating mere millions of kilometers from our Sun. 3I Atlas, the third such confirmed celestial body from beyond our solar neighborhood, has expelled streams of gas and debris extending 3 million kilometers, far surpassing the capabilities of any ordinary comet. This leads to a disquieting question. Did it simply fracture, scattering extraterrestrial material across our solar system? Or is this a deliberate action by something alien, something we have yet to comprehend? Tonight, we delve into the enigma, the science, and the astonishing possibilities. Although scientists assert there is no peril to Earth, by the conclusion, you will grasp the profound existential implications this alien visitor might present. Stay with us, for what transpires next transcends mere science. It is something for which we were entirely unprepared. If this mystery continues to captivate you as it has me, please ensure you press the like button and subscribe to Cosmo Chill so you do not miss a single update as this unfolds in real time. Share your location, the current time there, and your thoughts on this novel development in the comments section. To aid our community's expansion, please share this video on X, Facebook, Reddit, or even within your group conversations. Your support enables us to continue pursuing stories of this nature. Thank you for standing by us. Part 1. The Day the Sky Transformed. On the 9th of November, 2025, a cohort of astronomers meticulously compiled a series of deep space photographic records, revealing an anomaly that defied existence. Emanating from a singular point in the void were two colossal jets of matter. One extended approximately 1 million kilometers. The entity at the heart of this spectacle was designated 3I Atlas, and it had just become the most perplexing object within our solar system. It is crucial to grasp the magnitude of this situation. 3 million kilometers is roughly equivalent to 8 times the distance between Earth and the Moon. We are not discussing a minor puff of gas. We are contemplating structures of such immense scale that they dwarf interplanetary distances, erupting from what should be a comparatively diminutive fragment of ice and rock. When scientists first encountered these images, the primary inquiry was not merely, "What is this?" but rather, "What on earth happened?" 3I Atlas ranks as only the third unequivocally identified interstellar object to enter our solar system. Reflect on that for a moment. Throughout the entirety of human history, with all our telescopic capabilities and celestial surveys, we have confirmed only 3 visitors from beyond our cosmic vicinity. The first was Oumuamua, in 2017, that enigmatic, cigar-shaped entity that ignited countless discussions. The second was 2I Borisov in 2019, which, at least, behaved like a conventional comet. And now we have this object, discovered on the 1st of July, 2025, by the Atlas Survey operating in Chile. Its trajectory immediately signaled to astronomers that it was not indigenous to our system. Its orbit was hyperbolic, signifying its origin in interstellar space, its trajectory toward the Sun, and its eventual departure from our system, never to return. It was not gravitationally bound to our star like the comets and asteroids that originated here billions of years ago. This entity arrived from an entirely different location, bearing the chemical signatures of another stellar environment, another era, and a formation process we can only conjecture about. Initial estimations derived from Hubble Space Telescope imagery indicated that the nucleus, the solid core of 3I Atlas, measured approximately 5.6 kilometers in diameter. This is already substantial for a comet. For comparative purposes, Halley's Comet, arguably the most renowned comet in human cultural history, possesses a nucleus approximately 11 kilometers in length, though significantly less massive overall. However, here is where the situation becomes peculiar. Other data suggested that 3I Atlas might, in fact, be larger, potentially considerably so. The figures were not aligning, and this was prior to anyone recognizing the true peculiarity of this object. By standard statistical measures, within the frameworks we employ to predict the incidence of interstellar objects passing through our system, an object of this magnitude ought to be exceedingly rare. We are contemplating odds so remote that detecting one within a human lifespan should be an extraordinary event. Yet, here it was, substantial enough to be observed, luminous enough to be tracked, and exhibiting behaviors that prompted seasoned astronomers to employ terms such as unprecedented and inconsistent with established models. Then arrived the critical juncture. 3I Atlas achieved perihelion, its closest proximity to the Sun, around the 29th of October, 2025. Perihelion is the point when comets typically intensify in brightness and become active as solar heat vaporizes their icy components, forming their characteristic tail. However, the phenomenon observed with 3I Atlas was entirely unfamiliar. Shortly after perihelion, observers began to witness those immense jets, that peculiar dual plume structure, and a cascade of transformations suggesting a fundamental shift had occurred. Thus, the central question arises, the one that keeps scientists awake and their speculative papers filling preprint archives. What if 3I Atlas did not merely intensify and become active in proximity to the Sun? What if it actually fragmented, disintegrating under the strain of solar heating, tidal forces, and internal gaseous pressure? What if we are observing the remnants of an interstellar visitor, shattered into pieces, dispersing its alien contents across millions of kilometers of space? If this hypothesis holds true, if it indeed fractured, then we have been granted an extraordinary boon. Fragmented material signifies an augmented surface area, translating to more substance exposed to our telescopes and spectrometers. We may be examining the internal composition of an object formed around another star, potentially billions of years ago, subjected to cosmic ray bombardment over eons of interstellar transit, now laid bare for our analysis. It is akin to an extraterrestrial autopsy, except the subject spans millions of kilometers, and we are the investigators endeavoring to reconstruct its demise. However, another possibility exists, one that is less prominently featured in official reports, but carries greater weight in informal discussions and online forums. What if it did not fragment? What if 3I Atlas remains intact, and those jets, that energy output, those improbable measurements, are not attributable to passive ice sublimation? What if we are witnessing propulsion? What if we are observing technology? This is not yet a mainstream conclusion, nor is it a widely accepted hypothesis, but it is under consideration because the data stubbornly refuses to conform to the established paradigm of a typical comet. When observations necessitate either a radical re-evaluation of cometary physics or the contemplation of artificial origins, one enters uncharted territory. This is the realm where science intersects with philosophy and discovery borders on apprehension. The significance of this matter is profound, with implications extending in every direction. If 3I Atlas disintegrated, we gain unparalleled access to interstellar matter, refine our models, and deepen our understanding of how objects traverse the vastness between stars. If it did not disintegrate, if it is engaged in some other activity, then we may be observing the first confirmed technological artifact from beyond our solar system. And if that is the case, everything changes. So, what will transpire next? What will be the consequences for us, for Earth, and for our comprehension of the cosmos? If this interstellar visitor genuinely fractured near the Sun, or worse, what if it did not? Part 2, when the numbers defy logic. Let us examine precisely what the telescopes have recorded, for the intricacies lie entirely within the data. Following perihelion, observers worldwide began capturing images of 3I Atlas that bore no resemblance to a conventional comet. The dual jets were undoubtedly the most striking feature, but there was more. The structure of the tail was in constant flux. Amateur astronomers were disseminating images depicting what appeared to be plumes, as if the object were emitting material in irregular bursts rather than the steady outgassing expected from solar heating. Then there was the issue of color. Comets typically appear whitish or slightly yellowish due to reflected sunlight and the luminescence of ionized gases. At certain points, 3I Atlas exhibited a bluer hue than the Sun itself. This was not a subtle difference. It was a measurable and significant blueness, and the color continued to shift, changing over days and weeks in ways that did not correlate predictably with its distance from the Sun or any anticipated heating curve. It seemed as though the object was cycling through different operational modes or states, as if switches were being manipulated. Spectroscopy, the technique of dispersing light into its constituent wavelengths to identify chemical elements, revealed the next layer of strangeness. Both the James Webb Space Telescope and the SphereX mission directed their instruments towards 3I Atlas and detected a coma, the gaseous envelope surrounding the nucleus, overwhelmingly dominated by carbon dioxide. The measured ratio was astonishing. Carbon dioxide to water, approximately 8:1. For context, most comets within our solar system exhibit ratios closer to 1:10 or even 1:100, with water ice typically being the primary component. Here, carbon dioxide was the star, with water playing a mere supporting role. Why is this significant? Because it fundamentally alters the entire energy equation. Carbon dioxide sublimes, transitioning from solid to gas, at different temperatures and rates than water ice. Furthermore, it requires a specific quantity of solar energy to drive this sublimation process. When scientists calculated the volume of carbon dioxide being expelled by 3I Atlas, they encountered a perplexing issue. The surface area necessary to produce such an amount of gas, based on reasonable assumptions about solar heating and sublimation efficiency, was immense. We are referring to an effective absorbing surface area exceeding 1,600 square kilometers, which translates to a spherical object with a diameter of roughly 23 kilometers. However, the observed size, it will be recalled, was approximately 5.6 kilometers. The mathematical calculation did not reconcile. Either the object was substantially larger than Hubble images suggested, or the model was fundamentally flawed, or some other factor was at play. The rate of mass loss introduced another layer of confusion. Estimates indicated that 3I Atlas was expelling approximately 5 billion tons of material per month. Let that sink in for a moment. 5 billion tons every single month. The velocity of the outflow was estimated at about 0.4 kilometers per second, which is rapid, but not excessively so for sublimating gas. The perplexing aspect, however, was that the rate of mass loss was not constant. It was accelerating, and accelerating dramatically. In its initial approach, the object was losing perhaps 150 kilograms per second. Within a few weeks, this figure had escalated to 2 million kilograms per second. That represents an increase of over 10,000-fold. To account for such an acceleration using conventional cometary physics would necessitate a power law relationship with solar distance of approximately -10.5. This is an exceptionally steep exponent. Most comets adhere to power laws between -2 and -4. A value of -10.5 is beyond any typical range. What does this steep power law signify? It implies that the object's activity was far more sensitive to its distance from the Sun than any conventional comet should be. It suggests either a vastly different composition, a dramatic alteration in its structure, or that the underlying physics is no longer solely dependent on solar heating. This is the kind of measurement that prompts scientists to pause and meticulously re-verify their calculations, as its implications point towards something we do not fully comprehend. These anomalies converge to form a picture that resists clear resolution. High concentrations of carbon dioxide, insufficient surface area, extreme acceleration of mass loss, shifts in color, and non-gravitational acceleration, the latter indicating that the object's trajectory was being influenced by forces beyond the Sun's gravity, likely due to asymmetric outgassing, creating a rocket-like thrust. Individually, each of these phenomena could be explained by extending existing cometary models. However, collectively, they present a pattern of peculiarity that strains credulity. Fragmentation offers a potential explanation for some of these observations. If 3I Atlas fractured into multiple fragments near perihelion, the aggregate surface area would increase exponentially. Greater surface area translates to increased sublimation, leading to more gas, more substantial jets, and a higher rate of mass loss. Fragmentation could also account for the erratic behavior, the fluctuating tail structures, and the appearance of plumes and outbursts. Each fragment might sublimate at slightly different rates, tumble in unique ways, contributing to a chaotic overall display. However, fragmentation does not readily explain the color shifts, the pronounced dominance of carbon dioxide, or the precise timing of the surge in activity. It is a plausible hypothesis, perhaps the most compelling natural explanation, but it is not a perfect fit. And within that gap, within the space between what fragmentation can elucidate and what we are observing, the more unsettling possibilities begin to emerge. The data is irrefutable. The observations are robust. Multiple independent teams utilizing disparate instruments are witnessing the same anomalies. This is not a matter of erroneous calibration or a singular rogue measurement. 3I Atlas is genuinely exhibiting behaviors that push the boundaries of our current modeling capabilities based on known physics. We stand at the precipice, peering into a domain where either our understanding of comets requires a significant overhaul, or we are witnessing something that is not a comet at all. So, what is the typical behavior of comets, and how precisely does 3I Atlas deviate from this norm? That is what we will explore next. Part 3: Comets versus Alien Visitors, the Expectation Gap. Let us establish a baseline, for before one can fully appreciate the strangeness of 3I Atlas, one must comprehend what constitutes normal behavior. A standard comet is essentially a celestial snowball, a residual fragment of ice and rock from the early solar system. As it approaches the Sun, solar radiation warms its surface, causing volatile materials, primarily water ice, to sublimate directly from a solid to a gaseous state. This outgassing generates a hazy cloud known as the coma. Subsequently, the pressure exerted by sunlight and the solar wind propels that gas and dust away from the Sun, forming its characteristic tail. This is a passive process, entirely dictated by external energy input. The comet itself does not actively participate. It simply exists and undergoes vaporization. Typical comets within our solar system possess compositions that reflect their origins. They formed in the frigid outer reaches of our planetary system, where water ice was abundant. Consequently, water is the dominant volatile, accompanied by lesser quantities of carbon monoxide, carbon dioxide, methane, ammonia, and other simple molecules. When scientists analyze the gas emanating from these comets, the ratios are predictable. Water is predominant, followed by other substances. Their behavior is also predictable. Brightness increases as the comet draws nearer to the Sun, following smooth curves. Tails lengthen and shift based on the changing angle relative to the sun and the solar wind. Occasional outbursts may occur if a pocket of gas is suddenly released, but overall, the process is orderly. Now, consider 3I Atlas. Carbon dioxide is the dominant component. The ratio is inverted. Instead of water leading the process, carbon dioxide is present at 8 times the abundance of water. This is not merely unusual, it represents a complete inversion of the typical pattern. It suggests that this object originated in a vastly different environment, perhaps somewhere significantly colder or much richer in carbon dioxide ice than anything found within our solar system. Alternatively, it could imply that the surface has undergone chemical alteration through a process unseen in our celestial neighborhood. Then there is the sheer scale of the observed jets. While most comets do produce jets, they are generally modest, extending perhaps a few thousand to tens of thousands of kilometers. 3I Atlas, however, is generating jets that span millions of kilometers. This is akin to comparing a garden hose to a fire hydrant. Actually, no. It is more like comparing a garden hose to an industrial water cannon mounted on a dam. The volume and velocity of the expelled material are orders of magnitude greater than what any conventional comet can achieve. The tail structures are also highly peculiar. Comets typically possess 2 tails, a dust tail and an ion tail, which point in roughly predictable directions influenced by solar wind and radiation pressure. 3I Atlas has displayed multiple tails with configurations that change, structures that materialize and then vanish, and an overall morphology that evolves on a daily basis. It is as if the object is indecisive about its tail orientation, or as if multiple processes are vying for dominance. Let us revisit the issue of nuclear size, as it is central to understanding the discrepancy. To sublimate sufficient carbon dioxide to produce the observed jets and coma, a certain amount of surface area exposed to sunlight is required. The calculations are straightforward. One takes the solar flux at the comet's distance, multiplies it by the surface area, and factors in the efficiency with which carbon dioxide absorbs energy and sublimes, thereby yielding an estimated rate of mass loss. When scientists performed this calculation for 3I Atlas, the requisite surface area implied an object considerably larger than what Hubble imagery suggested. Fragmentation offers a potential resolution to this paradox. If the nucleus fractured into numerous smaller pieces, each fragment would possess its own surface area. Cumulatively, these areas could account for the necessary total surface area without necessitating a single, colossal nucleus. It is analogous to shattering a large rock into gravel. The total mass remains constant, but the overall surface area increases substantially because each small piece has its own exterior. Increased surface area leads to increased sublimation, resulting in larger jets. This hypothesis is plausible. However, does it provide a perfect explanation? Not entirely. Fragmentation should produce observable indicators. One would expect to see distinct multiple nuclei, separate origins for the jets. Observers have been scrutinizing the data, and although the information is complex and the object is distant, there is no clear consensus yet as to whether we are observing one nucleus or 16. Some analyses suggest multiple sources, while others indicate a single active core with asymmetrical outgassing. This ambiguity is frustrating. Then there is the alternative, one that does not rely on natural disintegration. What if 3I Atlas is not behaving like a conventional comet because it is not a conventional comet? What if those jets are exhaust? What if the color shifts are thermal signatures from active systems? What if the non-gravitational acceleration is a deliberate course correction? This is speculative, undoubtedly. However, it is speculation driven by the data's persistent refusal to conform neatly to any natural classification. To employ an analogy, imagine observing a bird flying overhead. One anticipates it to flap its wings, glide, or perhaps soar on thermal currents. Now, imagine this bird is emitting a blue glow, expelling fire from its tail, and moving in a straight line at 300 kilometers per hour without any visible means of propulsion. At a certain point, one ceases attempting to explain it as an unusual bird and begins to consider that perhaps it is not a bird at all. Perhaps it is a drone or something engineered. 3I Atlas is our glowing blue bird. The expectation was a comet. The observation is something that strains the definition of a comet to its breaking point. Either it is a comet exhibiting behaviors never before witnessed in such objects, in which case our models require substantial revision, or it is something else entirely, in which case our models are sound, but our assumptions about what exists beyond our solar system have been fundamentally shattered. So, where does this leave us? We have two primary scenarios under consideration. Scenario A posits a natural disintegration, the hypothesis of violent fragmentation. Scenario B suggests a surviving visitor, the possibility that this object remains intact and is engaged in activities that resemble engineering rather than purely physical phenomena. Let us explore the implications of each scenario. We begin with the disintegration. Part 4. Scenario A. The violent disintegration. Envision yourself as a 5-kilometer sphere of ice and rock that has spent millennia drifting through the galaxy. You have been bombarded by cosmic rays, struck by micrometeoroids, and chilled to near absolute zero for a duration exceeding the existence of human civilization. Now you are descending towards a star, and that star is irradiating you with an intensity you have never experienced. Your surface begins to heat. Your ices commence sublimation. Gas accumulates beneath your crust. The internal pressure escalates. The tidal forces exerted by the star's gravity begin to exert a stronger pull on your nearer side than your farther side. Something is bound to yield. This is the essence of the natural fragmentation hypothesis. Under extreme conditions in close proximity to perihelion, 3I Atlas could have simply fractured. The immense strain from solar warmth, coupled with the internal gaseous pressure stemming from rapidly vaporizing volatile substances and the gravitational pull exerted by the sun's tidal forces, could collectively overwhelm the structural integrity of the celestial body. Comets are not monolithic, solid entities. Instead, they are best described as accumulations of debris. These are loosely aggregated collections of smaller fragments held together by weak gravitational attraction and, perhaps, by ice functioning as a binding agent. Subjecting them to sufficient stress will cause them to disintegrate. We have observable instances of this phenomenon. The most renowned example is comet Shoemaker-Levy 9, which fractured into no fewer than 21 distinct pieces after venturing too close to Jupiter in the year 1992. These resultant fragments subsequently made a famous impact with Jupiter in 1994, generating spectacular impact marks that were discernible even through modest telescopes. It was Jupiter's potent tidal forces that tore Shoemaker-Levy 9 asunder. And while the comet 3I Atlas is not contending with the gravitational might of Jupiter, it is experiencing intense solar heating and a close approach to the Sun that could precipitate comparable outcomes. Should 3 Atlas fragment, the resulting pieces would disperse along the object's orbital path, creating an extensive stream of debris. These fragments would gradually drift apart, moving at subtly different velocities due to variations in their mass and the distinct propulsive effects generated by their individual gas emissions. The visual result would resemble a string of pearls, initially spanning dozens or hundreds of kilometers, eventually extending to millions of kilometers as the fragments diverge. Each individual fragment would possess its own surface area exposed to sunlight. This characteristic is paramount. A dramatic breakup substantially increases the total surface area relative to a given mass. Consider it akin to crushing an ice cube versus leaving it whole. The crushed ice melts more rapidly because a greater proportion of its surface is exposed to the warmer air. The underlying principle here is identical. An augmented surface area signifies increased sublimation, which in turn leads to greater gas production, consequently resulting in larger, brighter jets and a more active coma. The observed intensification of activity following its perihelion passage aligns perfectly with a fragmentation event that instantaneously amplified the effective surface area. Avi Loeb, the Harvard astrophysicist who has emerged as a prominent voice in discussions concerning interstellar objects, hypothesized in one of his online writings that 3 Atlas might have fractured into a minimum of 16 pieces. This specific number is derived from attempts to correlate the observed levels of activity with the necessary surface area. If one requires 16 times the surface area provided by a sphere measuring 5.6 kilometers in diameter, then approximately 16 fragments of comparable size, or a considerably larger number of smaller ones, would be needed. The mathematical estimation is approximate, but it affords an understanding of the magnitude involved. We are not contemplating a minor fissure. We are referring to a complete disintegration. What implications would such an event hold for Earth and the inner solar system? Let us begin with the favorable news. There is no threat of collision. 3 Atlas is following a hyperbolic trajectory that does not intersect Earth's orbital path. The object originated from interstellar space, executed a gravitational swing around the Sun, and is now proceeding back into the galaxy. Even if it were to fracture into 1,000 pieces, all those fragments would be traversing essentially the same trajectory, and that trajectory does not bring them into proximity with us. The closest approach to Earth is scheduled for December 19, 2025. However, even at that point, it will be millions of kilometers distant, far beyond any danger zone. The less favorable news, though still not posing a threat, is that fragmentation does generate a significant quantity of dust and small particulate matter. This material disperses, is influenced by solar wind and radiation pressure, and forms a diffuse cloud along its orbital path. Should Earth happen to traverse a dense region of this cloud, we might witness some faint meteor activity, akin to a very subtle meteor shower, with particles disintegrating harmlessly in the upper atmosphere. Space-based instruments, satellites, and telescopes could experience a marginal increase in dust impacts, but we are referring to microscopic particles at most. This would constitute an inconvenience, not a catastrophe. Interactions with the solar wind are also a possibility. Charged dust particles can influence the local plasma environment, inducing minor disturbances in magnetic fields and particle flows in the vicinity of the Sun. Scientists engaged in the study of solar physics and space weather might detect transient anomalies in their data, but again, nothing that poses a direct threat to Earth. From an observational standpoint, if 3 Atlas did indeed fragment, we should be able to detect evidence of this over the ensuing weeks and months. The morphology of its tail should continue to evolve as the fragments separate, giving rise to distinct plumes. High-resolution imaging might resolve multiple nuclei, appearing as discrete bright spots, where individual fragments are most active. The overall brightness could gradually diminish as the fragments recede from the Sun and their activity subsides. Dust trails should become increasingly elongated and diffuse. The temporal aspect is crucial. The closest Earth approach on December the 19th presents astronomers with an exceptional opportunity. The object will be relatively near in cosmic terms, which translates to superior angular resolution and more detailed imagery. If fragments are present, if there are multiple pieces, that is precisely when we are most likely to observe them clearly. Telescopes across the globe are already preparing for this date, scheduling observation time and calibrating instruments. It is akin to awaiting a jury's verdict. Scenario A, the violent fragmentation, represents the most scientifically sound interpretation. It necessitates no novel physics, no unconventional explanations. It simply describes a comet experiencing stress and behaving in a manner consistent with its known tendencies. It is, as scientists often term it, parsimonious, meaning it accounts for the observations with the fewest assumptions. However, parsimony does not guarantee veracity. Occasionally, the most straightforward explanation remains incorrect. Sometimes, reality proves more astonishing than the conservative prediction. Therefore, what if 3 Atlas did not fragment? What if it remains intact, and all the observed activity, the numerous jets, the seemingly impossible energy output, originates from an alternative source? This constitutes Scenario B, and it is within this scenario that matters become disquieting. Part 5. Scenario B, the enduring visitor. Let us consider the alternative, a scenario that causes scientific unease but cannot be entirely dismissed. What if 3 Atlas did not fracture? What if its nucleus remains intact, holding together despite the extreme conditions near the Sun and the observed jets, color shifts, and non-gravitational acceleration are all generated by something other than passive sublimation? What if we are witnessing propulsion? The indications are already present within the collected data. Non-gravitational acceleration signifies that the object's trajectory is being influenced by forces beyond mere gravity. For a comet, this is typically explained by the rocket effect, wherein gas sublimating from the surface is expelled in one direction, propelling the nucleus in the opposite direction, much like a miniature thruster. This is a standard phenomenon. However, the magnitude and pattern of 3 Atlas's acceleration do not conform to the usual profile. The deviations are too pronounced, too synchronized, suggesting deliberate guidance. Furthermore, there is the color shift. The object appeared bluer than the Sun, implying that it was emitting or reflecting light at shorter wavelengths, indicating higher energies. Typical cometary activity does not produce such an effect. Sublimation generates visible and ultraviolet light from excited gas molecules, but not in a manner that systematically shifts the overall color to a hue bluer than the solar spectrum. This would necessitate either a highly unusual chemical composition or an ancillary energy source, something that heats or energizes the material beyond the capacity of solar radiation alone. The issue of the energy budget is particularly significant. To generate jets as powerful as those observed, an exhaust velocity considerably exceeding the thermal speeds of sublimating gas is required. Sublimation typically yields velocities on the order of a few hundred meters per second at most. The jets emanating from 3 Atlas have been measured at 400 meters per second, which is already at the upper limit. However, to account for the observed thrust, the non-gravitational acceleration, one would ideally require exhaust velocities ranging from 3 to 50 kilometers per second. This is no longer indicative of sublimation, it points toward propulsion. This suggests the involvement of ion thrusters, chemical rockets, or some mechanism actively accelerating material. A.V. Loeb, in one of his online publications, articulated this starkly. Houston, we have a problem. The implication is evident. If 3 Atlas is intact, And if the jets originate from a singular body rather than multiple fragments, then the energy demand surpasses what solar heating can provide through conventional cometary processes. An alternative source is necessitated. This source would have to be engines. What might an intact, actively propelled interstellar craft resemble? Envision a probe, a vessel engineered for transit between stars, equipped with systems for trajectory adjustments, deployment of auxiliary units, and environmental study during its passage. Upon approaching a star, it might engage its propulsion systems to refine its course, utilizing stored energy or harnessing solar radiation. The observed jets could represent exhaust plumes from these systems, directed bursts of ionized gas or plasma. The color shifts might be thermal signatures indicating the cycling of its engines. The evolving tail morphology could be a consequence of different thrusters firing at various times, creating a complex and dynamic structure. This is, unequivocally, speculative. There is no definitive proof, no transmitted signal, no clear artifact, no irrefutable evidence. However, the possibility exists within the gap between our observations and what established natural physics can comfortably explain. If 3 Atlas is artificial, if it is technology, then we are not merely studying a comet. We are examining someone else's engineering, someone else's design, someone else's decision to dispatch an object into our solar system. What indicators would one seek if artificial origins were suspected? Firstly, an intact nucleus. If high-resolution imaging reveals a single cohesive body rather than multiple fragments, this would invalidate the natural breakup scenario and compel an alternative explanation for the observed activity. Secondly, synchronized jets. If the plumes are observed to be firing in patterns, if they are directional and timed, this would suggest deliberate control rather than random outgassing. Thirdly, subtle maneuvers. If the trajectory exhibits small, intentional alterations that do not align with sublimation-induced rocket effects, that would constitute a significant red flag. One would also look for recurring patterns. Does the object's brightness fluctuate in regular cycles? Does the color shift, repeat? Do the surges in activity correspond to specific distances or alignments? Natural processes can indeed produce periodicities, such as a rotating nucleus exposing different surfaces to sunlight. However, artificial systems might exhibit distinct signatures, different rhythmic patterns. It would be imperative to exhaust all natural explanations before asserting artificiality, yet instruments should remain prepared and data streams open, just in case. Then there is the matter of communication. If this were a probe, would it be transmitting signals? Would it be actively listening? Efforts to detect signals from 3 Atlas have thus far yielded no results. However, the absence of evidence does not equate to evidence of absence. It might be dormant. It could be utilizing frequencies or modulations that are not within our monitoring range. It might be designed for silent operation. Or it might simply be a celestial rock, and our perception of patterns within the noise stems from our inherent inclination to perceive agency and intention where none exists. The philosophical implications here are profound. If 3 Atlas is indeed technology, if it is artificial, then we are not alone, and we have just experienced our first confirmed contact with something constructed by another intelligence. This revelation would fundamentally alter our understanding of ourselves, our place in the cosmos, and our future trajectory. It would raise questions regarding intent. Why is it present? Is it observing us? Is its passage through our system a matter of chance or deliberate design? And if it is designed, what does that reveal about its creators? Even contemplating this possibility feels fraught with peril, akin to crossing a boundary between established science and speculative fiction. Yet, science has, in the past, ventured beyond such perceived boundaries and discovered reality on the other side. When quasars were first identified, some scientists briefly entertained the notion that they might be artificial beacons constructed by advanced civilizations. While this proved not to be the case, the question itself was deemed worthy of investigation. When pulsars were discovered, their remarkably precise radio pulses led astronomers to jokingly refer to the first one identified as LGM-1, an acronym for Little Green Men. It was eventually determined to be a neutron star, a natural celestial object, but the initial speculation was understandable given the data. 3 Atlas might represent a similar case, an unusual comet, nothing more. However, the data it presents is sufficiently anomalous, the irregularities sufficiently numerous, that the hypothesis of artificial origin cannot be summarily dismissed. Not yet, at least. Not until we obtain clearer imagery, more detailed spectral analysis, and more precise trajectory data. Not until December 19th, when the object reaches its closest approach, affording us our most intimate view. So, this is our current understanding. Scenario A posits fragmentation, driven by natural processes, a comet behaving as comets are wont to do under extreme environmental conditions. Scenario B proposes an intact object of artificial origin, exhibiting characteristics more aligned with engineering than with natural physics. Both scenarios remain viable. Both are supported by some evidence. Both also present challenges and unanswered questions. And the truth, irrespective of its nature, will undoubtedly reshape our perceptions of interstellar visitors, our understanding of the galaxy, and the fundamental question of our solitude. However, 3 Atlas is not the sole celestial anomaly currently under observation. Other narratives, other discoveries, and other challenges to our established assumptions are unfolding, all of which converge on this central theme. The universe is proving to be far more enigmatic than we had previously imagined, and we are only just beginning to comprehend the vastness of our ignorance. This is where our inquiry will proceed, into the intricacies of its chemical makeup, the mysteries surrounding its origin, and the broader implications of inhabiting a galaxy that consistently defies our preconceived notions. Part 6: Alien Ice, Cosmic Radiation, and Enigmatic Origins. Now we will delve into the chemical composition, for the makeup of 3 Atlas is as peculiar as its behavior, perhaps even more so. When the James Webb Space Telescope directed its infrared instruments towards the comet's coma, the spectral data returned was unlike anything observed from typical solar system comets. The ratio of carbon dioxide to water was approximately 8:1, as previously mentioned. This is an extreme deviation, but further examination reveals even greater strangeness. Spherex, another space-based observatory, corroborated these findings and provided additional details. The coma exhibited strong carbon dioxide emission, glowing intensely in the infrared wavelengths, where carbon dioxide molecules radiate after absorbing energy from sunlight. Water and carbon monoxide, other common volatile substances, were barely detectable. The production rates for water and carbon monoxide were orders of magnitude lower than that of carbon dioxide. It is as if this object is composed primarily of dry ice, with only a minute trace of frost. Polarimetry, a technique that quantifies the polarization of light after it interacts with material, introduced another layer of complexity. 3 Atlas displayed a pronounced negative polarization branch, reaching -2.7% at a phase angle of 7 degrees. For those unfamiliar with the term, this is a measurement indicating the degree to which the electric field of reflected light is aligned in a specific direction. Negative polarization branches are uncommon and typically signify very particular grain sizes and compositions within the dust and gas. The value measured for 3 Atlas is unprecedented among comets and asteroids, bearing no resemblance to anything in our existing catalog. So, what is the significance of all this? The elevated abundance of carbon dioxide suggests that 3 Atlas originated from a region within its parent protoplanetary disk where carbon dioxide ice was more stable than water ice relative to our solar system. This would correspond to the outer reaches, beyond the orbit of Neptune, where temperatures descend to levels at which carbon dioxide does not readily sublimate, while water ice still predominates. For carbon dioxide to be the dominant component, an even colder environment would be required, or one with a distinct initial chemical composition, enriched in carbon and oxygen, but deficient in hydrogen. This points towards a formation region situated far from the central star, or around a star with a chemical makeup different from our Sun. Additionally, there is the hypothesis involving cosmic rays. Over millennia of interstellar transit, an object such as 3 Atlas would be subjected to continuous bombardment by galactic cosmic rays, which are high-energy particles pervasive throughout the galaxy. These particles can penetrate several meters into ice and rock, breaking chemical bonds, forming new molecules, and altering the surface composition. One proposed mechanism suggests that cosmic rays transform carbon monoxide, which is commonly found in interstellar ice, into carbon dioxide through radiolysis, a chemical reaction driven by radiation. Over time, the outer layers of the object would become enriched in carbon dioxide, forming an organic-rich crust that differs chemically from its interior. This hypothesis of cosmic ray processing is compelling because it accounts not only for the high carbon dioxide content, but also for the unusual polarization signature. The crust would be composed of complex organic molecules and carbon-rich grains, materials that scatter light differently than pure ice or silicate dust. When these grains are expelled as part of the coma, they produce the observed polarization signature. This narrative is internally consistent, linking the object's composition to its protracted journey through interstellar space. However, it also raises further questions. If 3 Atlas has spent millions or even billions of years traversing the space between stars, where did it originally form? Every interstellar object possesses an origin, a star system where it coalesced, a planetary disk from which it condensed out of gas and dust. By analyzing its trajectory, astronomers can work backward and estimate the direction from which 3 Atlas originated within the galaxy. The results suggest that it did not originate from any star system in our immediate vicinity. It appears to have come from the general direction of the galactic center, or perhaps from a region of intense star formation located hundreds of light-years away. Pinpointing a precise source is exceedingly difficult, but the implication is that this object has been in transit for a very extended period, possibly since the early epochs of our galaxy, when star formation was more prolific and planetary systems were less stable. The object's composition also provides insights into the diversity of planetary systems. If 3 Atlas formed around another star, its chemistry reflects the conditions present in that system. The dominance of carbon dioxide indicates formation in a colder carbon-rich disk, perhaps one that originated from a molecular cloud with a higher metallicity or different isotopic ratios. It offers a glimpse into alien geology, alien mineralogy, and alien ice physics. Each measurement we obtain serves as a data point, contributing to our understanding of how planets and comets form elsewhere, thereby expanding our observational sample beyond the single instance observed in our own solar system. Furthermore, there is the question of population. If 3 Atlas is representative of a class of interstellar objects, bodies that have undergone radiation processing, possess organic-rich crusts, and exhibit high carbon dioxide content, then there could be numerous similar objects traversing the solar system undetected. Most would likely be too faint or too distant to be observed, particularly if they do not significantly brighten as they approach the Sun. Our current detection methods are inherently biased towards large, active objects. We are consequently missing the smaller, darker, and less active ones. 3 Atlas may well be the visible tip of an immense iceberg, a single luminous example within a population of thousands or millions that remain unseen. This has significant implications for our understanding of interstellar material exchange within the galaxy. Stars do not exist in isolation. They form in clusters, migrate through the galactic disk, and exert gravitational influence on each other's cometary reservoirs. Over billions of years, objects are ejected from one system and subsequently captured by another, or they simply drift through interstellar space, carrying with them the chemical signatures of their places of origin. The galaxy is in a perpetual state of rearrangement, mixing materials and exchanging fundamental building blocks. 3 Atlas embodies this ongoing process, acting as a messenger from another realm, conveying information encoded within its very atoms. The alien nature of its composition also lends credence to the more unconventional interpretations. If this object's chemical makeup is so profoundly different from anything found in our solar system, and if its crust has been transformed by cosmic rays into organic materials that we do not yet fully comprehend, then it is plausible that its behavior in proximity to the Sun might be equally extraordinary. The fundamental principles of physics might not fully explain its sublimation process, how it expels gas, or its reaction to solar radiation. It's possible we're attempting to apply models developed for celestial bodies within our own solar system to an entity that operates under entirely different conditions. Alternatively, and this is where the speculation becomes quite unsettling, its very composition might be intentional. Imagine constructing an advanced spacecraft for interstellar travel. You would select materials capable of enduring the extreme conditions of space for extended periods. This would include a protective outer layer to shield against cosmic rays, something that can either repel radiation or remain inert under its influence. Furthermore, you would need easily accessible volatile substances that could serve as fuel, stored in stable ice formations that vaporize predictably when near a star. Carbon dioxide perfectly fits these requirements. It possesses a high density, sublimes cleanly, and is chemically manageable. Therefore, a preponderance of carbon dioxide in its makeup might not be a natural occurrence, but rather a result of deliberate engineering. This is a significant leap, undoubtedly. There's currently no concrete proof indicating an artificial origin for its composition. However, once anomalies are detected in one aspect, such as its observed behavior, it becomes increasingly difficult to disregard unexpected characteristics in another, like its chemical makeup. These discrepancies mutually reinforce each other, building a compelling argument that 3I Atlas is fundamentally unlike anything we anticipate. The theory of cosmic ray processing offers the most plausible natural explanation for its composition, and it's a strong contender. It aligns with the available data, is supported by established physics, and is empirically verifiable. If we had the capability to directly sample its surface and analyze the organic outer layer in a controlled laboratory setting, we could either confirm or refute this hypothesis. Unfortunately, such direct investigation is beyond our reach. We are constrained to observing from millions of kilometers away, deducing its chemical properties from light particles and constructing models based on spectral analysis. This is akin to forensic investigation with incomplete evidence, and the final verdict remains undecided. What is evident is that 3I Atlas possesses a chemically alien nature. Whether this extraterrestrial quality stems from natural processes occurring in a different stellar environment, prolonged exposure to radiation over eons, or something far more calculated, remains unknown. However, its composition is crucial because it dictates the object's behavior, its responses to solar energy, and ultimately whether it disintegrates or remains intact. Thus, we have established that 3I Atlas exhibits peculiar chemical properties and anomalous behavior. This naturally leads to the next inquiry: its physical characteristics. If it were to fragment, what would be the precise mechanism of its breakup, and what would the resulting debris field resemble? This is where we now delve into the dynamics of fragmentation and its potential consequences. Part 7 will explore fracture, dust, and the formation of debris fields, addressing what might follow. The concept of fragmentation might sound straightforward, but the underlying mechanics are anything but. A comet is not a solid, monolithic structure. Instead, it's best described as a loosely aggregated collection of smaller fragments, pebbles, and larger rocks, bound together by ice and a weak gravitational pull. Its tensile strength, the force required to pull it apart, is minimal. Only a modest stress is needed to overcome its cohesion, provided that stress is applied with the correct intensity, at the right locations, and at the opportune moment. Solar heating emerges as a primary contributing factor. As 3I Atlas journeyed closer to the Sun, its surface temperature escalated dramatically. The ice on the sun-facing side commenced rapid sublimation, transitioning directly from a solid state to a gaseous one. However, this vaporization process is not uniform across the surface. Certain areas might be darker, absorbing more heat, while others could be coated with insulating dust, shielding the underlying ice. The outcome is uneven heating, creating localized hotspots and cold spots, along with thermal gradients that induce internal stress. Ice expands and contracts with temperature fluctuations. When these changes are abrupt and inconsistent, fissures develop. Then there's the matter of internal gas pressure. As volatile compounds vaporize beneath the surface, the resulting gas becomes trapped beneath layers of dust and less volatile ice. This trapped gas accumulates pressure. Eventually, the containment fails. The surface layer ruptures, releasing the gas explosively outward, carrying dust and fragments along with it. This phenomenon is responsible for the spectacular outbursts sometimes observed from comets, sudden surges in brightness as a pocket of gas is released instantaneously. If a significant volume of gas builds up and the structure is sufficiently weakened, the entire nucleus can shatter. Tidal forces introduce another significant element. The gravitational pull of the Sun is stronger on the side of the comet, closer to it than on the far side, creating a stretching effect. For a substantial object passing in close proximity to a massive celestial body, this tidal differential can be immense. This was the force that disassembled Comet Shoemaker-Levy 9 near Jupiter. 3I Atlas reached its perihelion at a distance of approximately 1.35 astronomical units, translating to about 135 million kilometers from the Sun. This distance is greater than that of Earth from the Sun. Consequently, the tidal forces exerted on 3I Atlas were not as extreme as they would have been if it had passed closer. Nevertheless, when combined with the internal stresses generated by heating and gas pressure, these tidal forces could still contribute to fragmentation. The object's rotational speed also plays a role. If the nucleus is spinning, the outward centrifugal force adds to the overall stress. Comets can rotate at considerable speeds, sometimes completing a full rotation in just a few hours. If 3I Atlas was already rotating and subsequently began expelling gas unevenly, these jets could act like miniature rocket engines, accelerating its rotation or altering its axis of spin. This further exacerbates the mechanical stress, increasing the likelihood of a breakup. Should fragmentation have occurred, the resulting pieces would initially remain in close proximity, perhaps separated by only a few kilometers. However, they would travel at slightly divergent velocities due to differences in their mass and the varying propulsive forces. Over the course of hours and days, these fragments would disperse along the comet's orbital path, forming a linear arrangement. Over weeks and months, this structure would extend to millions of kilometers, resembling a string of icy pearls slowly drifting apart. Avi Loeb's estimation of at least 16 fragments is derived from correlating the observed level of activity with the requisite surface area. If the original nucleus measured 5.6 kilometers in diameter, its surface area would have been approximately 98 square kilometers. To achieve 16 times that area, one would require either 16 fragments of comparable size or a significantly larger number of smaller ones. The precise count hinges on the nature of the breakup event, whether it was a clean division into substantial pieces or a chaotic disintegration into a cloud of fine debris. Each individual fragment would exhibit characteristics akin to a miniature comet. It would possess its own diffuse envelope, its own gas jets, and its own pattern of material expulsion. When viewed from a distance, the collective luminosity of all these fragments could create the impression of a single, expanded light source, appearing as a nebulous mass rather than distinct points of light. This could explain why observers have not yet definitively resolved multiple distinct nuclei. The fragments might be too closely clustered, individually too faint, or their light might be obscured by the overwhelming brilliance of the combined coma. The debris field would also encompass a significant quantity of dust. Fragmentation exposes fresh surfaces that sublimate at a faster rate, subsequently ejecting more dust. This dust then disperses, driven by the sun's radiation pressure, forming an expansive cloud along the orbital path. The particles vary in size, ranging from submicron-sized grains to pebbles measuring several millimeters. The smallest particles are propelled furthest from the sun, creating a fan-shaped distribution. Larger particles follow trajectories closer to the original orbital path. What are the implications of this for us? Earth's orbit does not intersect the trajectory of 3I Atlas, so we will not traverse its debris field. However, other spacecraft might. Satellites in high orbits, interplanetary probes, and solar observation platforms could potentially encounter stray dust particles. While the risk is minimal, it is not entirely negligible. A single dust grain impacting a sensitive instrument at interplanetary velocities can cause damage. Mission planners are cognizant of this risk and are actively monitoring the comet's trajectory and its predicted debris distribution as a precautionary measure. Furthermore, there is the factor of solar-wind interaction. Dust particles in space acquire electrical charges from ultraviolet radiation and collisions with plasma. Electrically charged dust can interact with the solar wind, a stream of charged particles emanating from the sun, particularly within dense dust clouds. This interaction can lead to localized disturbances in the magnetic field, detectable by instruments aboard spacecraft. Scientists studying space weather might observe anomalies in their data, subtle fluctuations that coincide with the comet's passage. Visually, from Earth, the debris field might not be particularly striking. The comet itself is already quite faint, requiring reasonably powerful telescopes for observation. If it fragments into numerous pieces, each fragment could be even fainter, making it more challenging to track. However, the combined illumination from multiple fragments could produce intriguing effects, such as an elongated tail or multiple distinct tail structures. Amateur astronomers equipped with backyard telescopes have been observing 3I Atlas, and some have reported witnessing alterations in the morphology of its tail. These observations suggest a level of complexity that could be indicative of fragmented pieces. The timing of observations is paramount. December 19, 2025, marks the date of 3I Atlas's closest approach to Earth, at a distance of approximately 0.6 astronomical units, roughly 90 million kilometers. This will present the most favorable opportunity for high-resolution imaging, spectroscopic analysis, and detailed characterization. If fragments are present, this is when they will be most clearly discernible. If the nucleus remains intact, this will be when we can most accurately measure its dimensions and form. Telescopes across the globe are coordinating their observation campaigns, scheduling time, and preparing their instruments. This represents a brief window of opportunity, a matter of mere days when the geometric alignment is optimal, after which the comet will continue its outward journey, fading into the distant expanse. What if the hypothesis of fragmentation proves to be incorrect? What if observations on December 19th reveal a single, intact nucleus with no indications of a breakup? In such a scenario, we would revert to scenario B, returning to the disquieting possibility that the observed activity, the expulsion of jets, and the energy output originate from a source other than natural sublimation. This leads us back to the hypothesis of artificiality, a line of speculation that persistently resurfaces. However, before fully embracing this speculative avenue, it is imperative to address the associated controversies, political considerations, and disputes over data access and scientific credibility. This narrative encompasses not only the comet or the probe or whatever 3I Atlas ultimately proves to be, but also the operational dynamics of scientific inquiry under pressure, the influence of transparency on public perception, and the stringent requirement for robust evidence when extraordinary claims are made. This will be the focus of the subsequent discussion. Part 8 delves into probes versus natural objects, technology, speculation, and the profound questions they raise. Let us acknowledge it directly. The hypothesis of artificial origin, the notion that 3I Atlas could be an artificial construct, a probe, an artifact, or something engineered by an external intelligence, is the undeniable elephant in the room. It represents the underlying possibility that fuels every anomaly, every piece of data that defies conventional explanation. While mainstream astronomers exercise caution and restraint, reluctant to engage in speculation without definitive evidence, such conjecture is indeed occurring across blogs, preprint publications, conference discussions, and within the collective public imagination. Avi Loeb has emerged as a leading proponent, advocating against prematurely dismissing the possibility of artificial origins. He is not an outlier. He holds a tenured professorship at Harvard, previously chaired its astronomy department, and is a respected theorist with a substantial publication record. Furthermore, he possesses a willingness to pose challenging questions and to question scientific consensus when empirical data warrants it. His involvement with Oumuamua, where he suggested it might be a solar sail, rendered him a polarizing figure. Some peers lauded his unconventional thinking, while others criticized him for venturing too far into speculation, perceiving it as sensationalism. With 3I Atlas, Loeb is posing similar inquiries. In his writings on the Medium platform, he has meticulously outlined the evidence. This includes the dominance of carbon dioxide, which deviates from established comet models. He highlights the energy budget conundrum, where the requisite surface area surpasses the observed dimensions of the object. He points to the non-gravitational acceleration, suggesting propulsion rather than passive outgassing. He notes color shifts that imply additional energy sources. He also flags the statistical improbability of an object of such magnitude originating from interstellar space. While each of these points might individually admit to a natural explanation, their collective pattern resists straightforward categorization. He has also drawn attention to the characteristics of its trajectory. 3I Atlas entered our solar system on a retrograde orbit, moving in opposition to the general direction of celestial bodies within our system. While not impossible for a naturally occurring interstellar object, this is a less common occurrence. The orbit also exhibits a rough alignment with the ecliptic plane, the flat disk where most planets reside. Again, this is not an impossibility, but it is statistically less probable for a random interloper from the galaxy. An engineer designing a probe to survey a solar system might opt for a trajectory that traverses the ecliptic, given its concentration of significant celestial bodies. Furthermore, Loeb employs terminology related to engine behavior. He has posited that jets exhibiting exhaust velocities in the range of 3 to 50 kilometers per second appear more indicative of propulsion than sublimation. Ion thrusters utilized by spacecraft such as Dawn and Deep Space One achieve exhaust speeds within this range by accelerating ions through electric fields. Chemical rockets are capable of even higher velocities. If 3I Atlas exhibits jets operating at these speeds, and if the nucleus is intact rather than fragmented, then an alternative explanation for the energy source becomes necessary. Solar heating alone would be insufficient. The phrase, "Houston, we have a problem," is not merely dramatic. It encapsulates Loeb's assertion that conventional models are inadequate, that a fundamental discrepancy exists, and that alternative explanations warrant serious consideration. These alternatives encompass exotic natural processes, certainly, but they also extend to the possibility of technological intervention. What would constitute irrefutable proof? This is the critical question. Speculation is facile. Proof is arduous. If one were to definitively demonstrate that 3I Atlas is artificial, what evidence would be sought? A radio signal would serve as definitive proof, a directed transmission within a narrow frequency band that cannot be attributed to natural emissions. Scientists have employed radio telescopes to search for signals emanating from 3I Atlas. To date, no such signals have been detected. However, the absence of evidence is not indicative of the absence of a phenomenon. It is possible that it is not transmitting, or that it is using a frequency or modulation scheme that is not currently being monitored. Optical signals would provide another crucial clue. Deliberate flashes, pulses, or patterns in brightness that do not correlate with rotation or outgassing would be highly significant. Thus far, observed variations in brightness appear consistent with a nucleus that is rotating and exhibiting asymmetrical activity. Nevertheless, subtle patterns might be concealed within the noise, awaiting more meticulous analysis. Trajectory adjustments would be compelling evidence. If the object executed a course correction, a deliberate alteration in velocity that cannot be attributed to gravitational interactions or outgassing, it would be exceedingly difficult to explain through natural phenomena. Continuous monitoring of its orbit over months and years will be essential. Minor deviations from its predicted path could hold significant implications. Then there is the question of intent. If this object is a probe, what is its purpose? Is it conducting reconnaissance of our solar system? Is its presence a matter of chance, a mere transit? Is it a derelict remnant of an ancient mission now drifting aimlessly? Is it actively engaged in studying us, collecting data, and transmitting information back? Or does it serve a different function entirely? perhaps as a component of interstellar infrastructure, a navigational beacon, or a warning marker. The range of possibilities expands considerably once the artificial hypothesis is entertained. The public's fascination is palpable. Celebrities have voiced their opinions. Kim Kardashian, for instance, posted about Three-Eye Atlas on social media, questioning if it represented evidence of extraterrestrial life. Joe Rogan discussed the topic on his podcast, inviting speculation from his vast audience. News coverage has spanned from popular entertainment magazines like People to tabloid publications such as the New York Post, and even to more serious scientific journals. The fervor surrounding this object is undeniable, and it generates a dual effect. On one hand, public interest can stimulate funding for astronomical research and encourage the organization of observation campaigns, thereby drawing attention to the field of astronomy. On the other hand, it can foster pressure to arrive at sensational conclusions, prioritizing speculation over scientific rigor and potentially poisoning the atmosphere of scientific discourse. Scientists find themselves in a precarious position. They must maintain their credibility, which necessitates a cautious and conservative approach, refraining from making assertions that lack substantiation. Simultaneously, they must be forthright about the existing uncertainties and the fact that Three-Eye Atlas does not fit neatly into established categories. While stating "we don't know" is scientifically accurate, it is often unsatisfying and creates a vacuum that others may fill with more extravagant theories. The risk associated with excessive speculation lies in the potential forfeiture of credibility should one's predictions prove incorrect. Loeb has experienced this firsthand. His hypothesis regarding Oumuamua as a solar sail attracted considerable criticism. While some of this critique stemmed from legitimate scientific disagreements, a portion was personal, targeting his motivations or competence. He has developed a degree of resilience, yet the dynamic itself remains detrimental. Scientific progress is best facilitated when individuals can propose ideas without fear of career repercussions. However, it is also essential to have mechanisms in place to effectively filter out unsubstantiated claims and to distinguish between speculation and evidence-based assertions. Nevertheless, the potential reward, should the artificial hypothesis prove to be true, would be immeasurable. Confirmation of extraterrestrial technology, even a derelict probe, would represent the most significant discovery in human history. It would definitively establish our solitude as a misconception, proving that intelligence has indeed emerged elsewhere and that civilizations exist, or have existed, beyond Earth. This would fundamentally reshape philosophy, religion, culture, and political landscapes. It would provide us with a crucial point of comparison, a benchmark against which we could measure our own existence and gain insight into the broader possibilities of cosmic existence. It would herald the dawn of a new epoch. However, we have not yet reached that juncture. We currently find ourselves in a complex transitional phase where the data is ambiguous, interpretations are contested, and the ultimate truth remains elusive until more refined observations become available. December 19th is approaching. The telescopes are prepared. The questions are becoming more focused. And regardless of what we learn, whether Three-Eye Atlas is merely a fragmented comet or something more enigmatic, the answers will hold profound significance. For the present moment, the speculation surrounding its technological nature remains just that, speculation. However, it is informed speculation, driven by genuine anomalies and empirical data that challenge our established models. And this, even if it induces discomfort, warrants our attention. The subsequent segment of this narrative will not focus on the object itself, but rather on the processes involved, the political considerations, the disputes over data access, and the extent of transparency within the scientific community when addressing extraordinary claims. This is the direction we will now proceed. Part 9 examines the question of who controls the imagery, the intersection of politics, data, and the crucial element of scientific trust. Science endeavors to present itself as an objective discipline, characterized by transparency and guided solely by evidence and rational deduction. And in its ideal state, it is precisely that. However, science is ultimately conducted by human beings operating within institutions that are susceptible to political influences, ego, and competition. When an anomaly as peculiar as 3I Atlas emerges, these human elements invariably come to the forefront, and the struggle for access to data becomes nearly as compelling as the object under scrutiny itself. Here is the current situation. A multitude of observatories have been actively studying 3I Atlas since its initial detection. Ground-based telescopes located in Chile, Hawaii, Arizona, and other regions have meticulously tracked its movement, capturing images and measuring its luminosity and spectral characteristics. Space-based instruments, including the Hubble Space Telescope, the James Webb Space Telescope, and SphereX, have provided invaluable infrared and ultraviolet data. Furthermore, amateur astronomers worldwide have contributed their own observations, effectively filling observational gaps and ensuring continuous coverage that professional telescopes, with their limited operational time, cannot consistently achieve. However, not all of this collected data is immediately accessible to the public. A portion of it is proprietary, retained by research teams who are granted exclusive access for a designated period to conduct their analyses and publish their findings. This practice is standard within the field of astronomy. Observing time on telescopes is a highly valuable and competitively sought-after resource, and the teams that successfully secure this time are given priority in accessing and interpreting the data. The underlying rationale is to acknowledge and reward the effort, expertise, and resources invested in making these observations, allowing researchers adequate time for thorough analysis before releasing raw data that could be prone to misinterpretation or premature disclosure by others. The complication arises when the celestial object in question is so unusual, so potentially significant, that the public's desire for immediate answers surpasses the standard scientific protocols. Individuals are eager for answers without delay. They wish to examine the images, scrutinize the spectral data, and evaluate the evidence for themselves. When data is withheld, even for legitimate scientific reasons, suspicion begins to germinate. Are certain findings being deliberately concealed? Are scientists engaging in a cover-up of evidence? Is there an orchestrated conspiracy to suppress the truth about extraterrestrial visitors? That lingering question reached its zenith when a United States legislator, spurred by appeals from constituents and widespread public intrigue, formally lodged a request for NASA to declassify high-resolution imagery of 3I Atlas, captured by the high-rise camera aboard the Mars Reconnaissance Orbiter. "Hold on," you might interject. "High-rise is engineered for planetary photography, not celestial bodies like comets." That much is accurate, but the camera boasts extraordinary visual acuity. If directed towards 3I Atlas during an opportune celestial alignment, it possessed the potential to discern surface details or multiple nuclei that other instruments might fail to resolve. The official rationale for denying the request was that the high-rise instrument was not authorized for such an observation, and reallocating resources would jeopardize ongoing Martian scientific endeavors. Nevertheless, this refusal fueled conjecture that NASA possesses extraordinary imagery of the object and is deliberately concealing it. There is no substantiated evidence to support this conspiracy. It is highly improbable that HiRISE has ever imaged 3I Atlas, and even if it had, the immense distance and geometric constraints would render the resolution of fine details virtually unattainable. Yet, this incident aptly demonstrates the inherent friction between the methodical progression of scientific inquiry and the public's demand for unhindered access to information. When confronted with phenomena that could conceivably represent the inaugural confirmed instance of extraterrestrial engineering, conventional scientific protocols appear insufficient. Peer assessment represents another contentious arena. Numerous findings pertaining to 3I Atlas have initially surfaced as preprints, which are scholarly articles uploaded to repositories like arXiv prior to formal peer review and publication in academic journals. Even more informal are the blog posts authored by Avi Loeb, which lean more towards public discourse than rigorous scientific dissemination. This is not inherently detrimental. Preprints facilitate the rapid dissemination of discoveries, and blog posts can effectively convey complex ideas to a wider audience. However, they bypass the crucial quality control mechanisms inherent in peer review. This can lead to the propagation of errors, the presentation of speculation as established fact, and difficulties for non-expert readers in differentiating credible analysis from unsubstantiated theories. The fundamental challenge lies in the time-consuming nature of peer review, which can often extend for months or even years. For an object as transient as 3I Atlas, awaiting formal publication translates to falling behind the observational timeline. By the time a peer-reviewed paper emerges, the comet may have receded beyond the range of effective observation, or subsequent data might render the initial analysis obsolete. Consequently, researchers find themselves caught between the imperative for swiftness and the necessity for meticulous scrutiny. The public's confidence in scientific endeavors is also at stake. The general populace is observing, consuming headlines, and forming opinions. If scientists appear reticent, if they withhold data, or if they communicate in a specialized jargon that obfuscates rather than clarifies, public trust erodes. Conspiracy theories thrive in environments characterized by information scarcity or inconsistency, and once trust is compromised, its restoration proves exceedingly difficult. The involvement of celebrities further complicates matters. When Kim Kardashian addresses her hundreds of millions of followers on Twitter regarding 3I Atlas, or when Joe Rogan dedicates segments of his podcast to speculating about alien probes, the narrative transcends scientific oversight. These individuals possess a reach and influence far exceeding that of any astronomer. Their commentary, irrespective of their intentions, can amplify misinformation, cultivate unrealistic expectations, or trivialize profound scientific questions. Simultaneously, the attention garnered by celebrities draws both eyes and minds to the subject matter. It elevates public awareness of astronomy, the ongoing search for extraterrestrial intelligence, and the enduring mysteries of our universe. It can inspire young individuals to pursue scientific careers, to pose significant questions, and to gaze at the heavens with a sense of wonder. The art lies in harmonizing enthusiasm with accuracy and hyperbole with humility. Proponents of open data advocate that enhanced transparency would resolve many of these prediculations. If all astronomical observations were promptly made accessible to the public, and if raw data were freely available, then independent analysts, amateur astronomers, and crowdsourced initiatives could contribute significantly to scientific progress. This approach has yielded considerable success in the past. Galaxy Zoo, a project that enlisted volunteers to classify galaxy shapes, led to discoveries that eluded professional astronomers. Citizen scientists have identified exoplanets, tracked asteroids, and contributed to innumerable research endeavors. However, open data also carries inherent risks. Not every individual possesses the requisite expertise to interpret complex datasets. Misinterpretations can proliferate rapidly, fostering confusion or propagating erroneous narratives. There is also the issue of intellectual property. If a research team dedicates years to developing instruments, planning observations, and analyzing data, only to have their findings preempted by another party who swiftly processes publicly released information, it can be profoundly disheartening and fundamentally unfair. The history of preceding interstellar objects offers valuable lessons. Upon the discovery of Oumuamua in 2017, the data was relatively accessible, prompting numerous teams to publish analyses. This openness fostered vigorous debate, competing interpretations, and ultimately a prevailing consensus that Oumuamua was likely a natural, albeit peculiar, celestial body. However, it also gave rise to fringe assertions, sensationalized headlines, and enduring controversies, particularly concerning Avi Loeb's light sail hypothesis. Borisov, the second confirmed interstellar visitor, presented a more straightforward profile, exhibiting behavior akin to a typical comet, and the scientific community's response was notably calmer and more measured. 3I Atlas appears to be diverging from the Borisov model and trending more towards the Oumuamua trajectory. The anomalies observed are too significant to disregard, and the questions posed are too profound to dismiss. This implies that the political discourse, the scientific debates, and the contests over data and interpretation will inevitably persist. The paramount concern remains the continuation of observations, the application of the most rigorous analytical methods possible, and the commitment of scientists to communicate with unvarnished honesty regarding their knowledge, their uncertainties, and the spectrum of potential explanations. Should 3I Atlas ultimately prove to be a fragmented comet, that outcome would be acceptable. We would have gained valuable insights into interstellar objects and refined our existing models. However, if it transpires to be something more unusual, then the degree of transparency and rigor with which the discovery is managed will dictate whether it is remembered as a triumph of scientific endeavor or a cautionary tale of squandered opportunities. For the present moment, observational data continues to accumulate. December 19th looms, and the world remains attentive. Yet, the narrative surrounding 3I Atlas is not unfolding in isolation. The cosmos has recently presented other astonishing revelations, other challenges to our preconceived notions, and other intimations that the universe is far more enigmatic and dynamic than we previously comprehended. It is to these broader cosmic contexts that we now turn our attention, shifting our focus from this solitary object to a more expansive perspective. Why does this particular entity hold such significance? What insights does it offer regarding astronomy, humanity's place within the grand tapestry of existence, and our position within a galaxy that consistently defies expectations? This constitutes the final segment of our inquiry, and it is to this crucial aspect that we now proceed. Part 10. The Significance of 3I Atlas, a Grand Perspective for Astronomy and Humanity. Let us pause and take a step back to adopt a wider viewpoint. Since humanity embarked on its earnest exploration of the celestial sphere, dating back to Galileo's pioneering use of the telescope, and Edwin Hubble's revelation that seemingly nebulous patches were, in fact, entire galaxies, we have consistently discovered that the universe is vaster, more ancient, and more extraordinary than we had ever imagined. Each successive generation harbors the belief that they have largely deciphered the cosmic puzzle, only to be proven demonstrably incorrect by subsequent observations. 3I Atlas stands as the most recent in a long lineage of discoveries that compel profound humility. Only 3 interstellar objects have been definitively confirmed entering our solar system. Across the entirety of recorded human observation, a mere 3. First, Oumuamua in 2017, distinctly cigar-shaped and rotating, defying straightforward classification. Second, Borisov in 2019, more cometary in appearance, less perplexing, yet undeniably an outsider. And now, 3I Atlas, the largest and most anomalous of the trio, pushing the very boundaries of our explanatory capabilities. Consider the sheer improbability of these encounters. Interstellar space is an expanse of unimaginable emptiness. Stars are separated by light years, distances so immense that even travel at speeds approaching that of light would require decades or centuries to traverse. Objects ejected from one star system drift for millennia, often millions of years, before encountering another. The statistical probability of detecting one such object passing through our relatively modest cosmic neighborhood during our own comparatively brief observational window is exceedingly low. And yet, we have now documented 3 such instances. What does this imply about the population of such objects? If our contemporary surveys have detected 3 in less than a decade, how many are evading our detection? Estimates vary considerably, but some models suggest that thousands of interstellar objects could be traversing the inner solar system at any given moment. The vast majority are likely too diminutive or too faint for us to perceive. With advancements in observational surveys, more sophisticated instruments, and dedicated search programs, the rate of detection is poised to increase. 3I Atlas may well be the herald of a veritable flood. If interstellar objects are indeed commonplace, and if the galaxy is in a perpetual state of material exchange between its star systems, then our prevailing models of solar system formation and evolution require substantial revision. We have heretofore conceptualized our solar system as an isolated entity, a self-contained unit shaped exclusively by internal processes and the infrequent intrusion of comets or asteroids originating from our own Oort cloud or Kuiper belt. However, if interstellar visitors are frequent, and if they introduce chemicals and materials from other stellar environments, then a continuous mixing process is underway. Our solar system is not a closed system. It is an integral component of a galactic ecosystem, engaged in the exchange of matter and information across immense temporal scales, a concept with profound philosophical implications. We are not isolated. We are not solitary. Even in the absence of confirmed intelligent life, the constituent molecules of 3I Atlas were forged within a different stellar nursery, shaped by the illumination of another star, and processed by the same cosmic forces that sculpted our own existence. There exists a fundamental continuity, a profound connection that spans the entire galaxy. And if matter can traverse the vast distances between stars, if the processes of chemistry and geology are indeed galactic in scope, then perhaps life itself possesses the capacity for such interstellar travel. Panspermia, the hypothesis that life might propagate across worlds via comets or asteroids, gains considerably more plausibility under this paradigm. It is conceivable that the fundamental building blocks of life, or even rudimentary organisms, could hitch a ride on interstellar objects, seeding new planetary bodies. This could be the very mechanism by which life originated on Earth, or how it spreads throughout the cosmos. 3I Atlas also holds significance for its contributions to our understanding of planetary defense and future space exploration. If interstellar objects are indeed common, and if they can enter our solar system on trajectories that are inherently unpredictable, then their tracking becomes an imperative. While the majority will pose no threat to Earth, statistical probabilities dictate that eventually one might. The ability to detect such objects early, to characterize their orbital paths, and to accurately assess potential risks are practical considerations that extend far beyond purely scientific inquiry. Furthermore, if humanity entertains the prospect of dispatching its own probes to distant stars, missions such as Breakthrough Starshot, which aims to accelerate minuscule spacecraft to a significant fraction of the speed of light, then comprehending the potential encounters such probes might face en route is absolutely critical. Interstellar space is far from empty. It contains dust, gas, radiation, and, as 3i Atlas demonstrates, solid objects of sufficient size to obliterate a spacecraft upon impact. 3i Atlas provides invaluable data concerning the composition of these interstellar visitors, their velocities, and the expected characteristics of objects encountered in the vastness between stars. However, the most profound reason for the significance of 3i Atlas lies deeper, touching upon existential questions. It compels us to confront ambiguity and to embrace the inherent discomfort of the unknown. Is it a comet? Is it technology? Is it something for which we currently lack the vocabulary? While the definitive answer is undeniably important, it is the process of inquiry itself, the willingness to entertain possibilities that challenge our established worldview, that fosters growth. It is in this process that science transcends mere data collection, transforming into a mode of thinking, an attitude of openness to surprise, and a capacity to revise our beliefs in light of compelling evidence. If 3i Atlas is indeed a fragmented comet, we will have learned that interstellar bodies can undergo dramatic fragmentation when approaching the Sun. We will have gained knowledge of the existence of naturally occurring compositions dominated by carbon dioxide. We will understand how cosmic ray processing can form organic crusts on celestial bodies that traverse the galaxy. These are invaluable discoveries, refining our models, providing new data points, and expanding the scope of our comprehension. If, however, 3i Atlas remains intact and exhibits more peculiar behavior, if there exists even a remote possibility of it being artificial in origin, then the implications become exponentially more profound. The conclusion that we are not alone would be solidified, meaning would have transcended the confines of Earth. Intelligence would exist, or have existed, elsewhere, and we would have achieved our first confirmed interaction with it. Such a revelation would fundamentally alter our perception of ourselves, our outlook on the future, and our species' priorities. It would represent not merely an astronomical discovery, but a civilizational turning point. Even if a definitive answer remains elusive, even if 3i Atlas eventually recedes into the distant void, leaving us with more questions than answers, the very exercise holds intrinsic value. We have pushed our instruments to their absolute limits. We have engaged in rigorous debates over interpretations, honed our methodologies, and fostered collaboration across institutions and national borders. We have captivated the public imagination, ignited curiosity, and reminded people that the universe remains an inexhaustible source of mystery. These outcomes are immensely valuable, indeed, invaluable. The ongoing saga of 3i Atlas continues to unfold. December 19th promises to deliver new data. Subsequent observations, spanning months and years, will meticulously track its evolution, its trajectory, and its ultimate destiny. Scholarly papers will be published, subjected to scrutiny, and revised. A scientific consensus may emerge, or the ongoing controversy might intensify. Regardless of the ultimate outcome, this celestial object has already left an indelible mark. It has compelled us to think more deeply, to observe more closely, and to question more profoundly. And it is not alone in this capacity. The universe has, in recent times, presented a series of other astonishing revelations, other discoveries that challenge our established assumptions and broaden our understanding of the cosmos. Three-Eye Atlas is but one element within a larger pattern, a juncture in time where our observational capabilities are advancing at an unprecedented pace, and the universe is revealing itself in ways that far exceed our initial predictions. It is to these parallel narratives, these other recent breakthroughs that complement and contextualize this enigmatic visitor from the void, that we now turn our attention. Part 11. The universe is cooling, a decline in star formation. While the spotlight has predominantly been on Three-Eye Atlas, dominating headlines and occupying valuable telescope time, a separate cosmic narrative has been quietly reshaping our understanding of the universe's past, present, and future. One of the most significant developments originates from the Euclid mission, a sophisticated telescope launched by the European Space Agency in 2023, tasked with meticulously mapping the large-scale structure of the universe and investigating the enigmatic nature of dark energy. The most recent data release from Euclid, which became publicly available in 2025, contains findings that may have been overlooked amidst the fervor surrounding the comet. The rate at which stars are forming throughout the universe has reached its peak and is now demonstrably in decline. The cosmos, in essence, is gradually cooling down. While this assertion may not initially strike as dramatically significant, its implications are profound. For billions of years following the Big Bang, the universe was characterized by an intense period of stellar genesis. Vast nebulae of hydrogen and helium, under the relentless force of gravity, collapsed and ignited nuclear fusion, giving birth to the very first stars. These stellar entities lived out their life cycles, eventually culminating in supernova explosions, a process that enriched the interstellar medium with heavier elements. From this enriched material, new generations of stars began to form, leading to the creation of planets, moons, and ultimately, the conditions conducive to the emergence of life. Star formation served as the principal engine of cosmic evolution, the transformative process that converted simple gaseous elements into intricate structures. This rate of formation was not static. It reached its apex approximately 10 billion years ago during the universe's Middle Age, a period marked by frequent galactic collisions that triggered prodigious bursts of star formation within galactic cores and spiral arms. Since that epoch, the rate has been in a state of gradual decline, initially slow, but now increasingly noticeable. Euclid's data unequivocally demonstrates that fewer new stars are currently forming than at any prior juncture in recent cosmic history. The universe is transitioning into a more quiescent phase, where existing stars are aging and dissipating, and fewer nascent stars are emerging to replace them. The underlying causes for this phenomenon are multifaceted. A primary factor is the depletion of raw materials. Hydrogen gas, the fundamental fuel for stellar creation, is being progressively consumed by existing stars or is sequestered within galaxies where conditions are no longer conducive to gravitational collapse. Dark energy, the mysterious force responsible for the accelerating expansion of the universe, also plays a significant role. As space expands at an ever-increasing rate, galaxies are progressively drifting apart, diminishing the frequency of collisions and, consequently, reducing the gravitational interactions that are essential for triggering star formation. The implications of this trend are far-reaching. A reduction in the formation of new stars directly correlates with a decrease in the creation of new planetary systems. This suggests that the future universe will be characterized by greater darkness and colder temperatures, with a dominance of aging stars and stellar remnants. Consequently, opportunities for life, at least life as we currently understand it, will become increasingly scarce. We are presently inhabiting an era where star formation remains sufficiently robust to facilitate the genesis of Earth-like worlds, yet this era is finite. Billions of years hence, the universe will be a profoundly different place, dimmer and more static. How does this cosmic trend connect to 3I Atlas? On the surface, the two phenomena appear entirely unrelated. One involves a singular celestial object traversing our solar system, while the other represents a universal trend spanning billions of light years. However, both challenge the long-held assumption of a universe in a steady state, the notion that the cosmos has always been and will forever remain as it appears to us now. Just as 3I Atlas exhibits behavior inconsistent with that of a conventional comet, the universe itself is not perpetually operating as an unceasing stellar factory. Both serve as potent reminders that change is an intrinsic and fundamental aspect of cosmic existence, and that nothing within the universe is truly static. Furthermore, there exists a thematic resonance between these two disparate observations. If star formation is on a decline, and if the creation of new planetary systems is becoming increasingly rare, then interstellar objects, such as 3I Atlas, may represent an increasingly vital mechanism for the exchange of materials between pre-existing systems. As galaxies age and stellar nurseries diminish in activity, the objects already present within them, comets, asteroids, and potentially artificial probes, emerge as the primary carriers of information and chemical compounds. The emphasis shifts from the act of creation to the process of circulation, from the genesis of new entities to the recycling of existing ones. This also necessitates a re-evaluation of our detection strategies. If interstellar visitors are becoming more prevalent, not due to new stellar activity, but rather as a consequence of numerous aging star systems shedding their constituent materials, then we should anticipate encountering more objects akin to 3I Atlas in the future, not fewer. It is plausible that the galaxy is entering an epoch where the predominant activity is exchange rather than formation, with wandering bodies serving as conduits for the legacy of declining systems to reach younger ones. The findings from the Euclid mission also underscore a fundamental aspect of observation and temporal positioning. We inhabit a universe estimated to be approximately 13.8 billion years old, and our observations are occurring at a specific transient moment in its evolutionary timeline. This particular moment in cosmic history falls after the peak of star formation, but predates the universe's descent into complete darkness. We are, in essence, situated within a cosmic twilight, observing the gradual winding down of stellar engines, though they have not yet been fully extinguished. 3I Atlas is passing through our solar system during this same twilight phase, a visitor from a galaxy where star formation peaked billions of years ago, where the objects drifting through space may represent the final remnants of once vibrant planetary systems. There is a profound poignancy to this observation if one considers it deeply. The universe experienced its exuberant youth, its period of peak productivity, and is now gradually settling into a long, slow decline. This is not indicative of a collapse or an impending end, but rather a gradual fading. Star formation will undoubtedly continue for billions of years to come, but the epoch of its greatest intensity has passed. We are living in the aftermath of the universe's most active phase, and objects like 3I Atlas are, in a sense, messages in bottles from that earlier era, carrying invaluable information about what transpired before. This realization aligns with a broader understanding that has been steadily emerging within the field of astronomy over the past several decades. The universe is not behaving as we had initially conceived. It is not static, nor is it stable, nor is it predictable in the manner suggested by our theoretical frameworks. Dark energy is accelerating cosmic expansion, contrary to our expectations of deceleration. Star formation is declining when we had assumed it would persist indefinitely. And now, with the advent of 3I Atlas, even our understanding of comets and interstellar objects is being fundamentally challenged. The overarching pattern is unmistakable. Every time we intensify our observational scrutiny, the universe presents us with novel surprises. Every time we develop more sophisticated instruments, we uncover phenomena that defy our existing theoretical models. The paramount lesson derived from these encounters is humility. This lesson extends far beyond the realm of astronomy. If the universe, at its grandest scales, is exhibiting unexpected behavior, if the intricate machinery of galactic evolution and cosmic expansion is more complex than we had previously comprehended, then why should we anticipate simplicity at smaller scales? Why should a singular interstellar object adhere strictly to predicted behaviors? While the connection between the macrocosmic and the microcosmic may not be one of direct causality, it carries significant philosophical weight. Both realms point towards a singular, profound truth. Reality is far richer, more enigmatic, and more layered than our current theoretical constructs can fully encompass. We constantly find ourselves playing catch-up, continuously refining our understanding and realizing that what we once considered stable ground is, in fact, perpetually shifting. The revelations from Euclid regarding the decrease in star formation serve as a potent reminder that the cosmos possesses a profound history and an unfolding future, and we are merely observing a specific segment of this grand narrative. 3 Atlas embodies this same era, a transient visitor from a different part of the universal saga, carrying vital clues about our galaxy's past and its trajectory. Both instances underscore the transient nature of all things, the unwavering constancy of change, and the extraordinary value of our brief epoch in cosmic history, a moment both precious and ephemeral, demanding our full attention. Yet the surprises do not cease there. If the rate of stellar genesis is indeed waning, then another foundational tenet of our understanding of the universe is also facing scrutiny, this time concerning the very nature of cosmic expansion itself. This constitutes the subsequent piece of this intricate puzzle. Part 12. Is the universe's expansion decelerating? For more than 2 decades, cosmologists have operated under a paradigm-altering discovery. In the year 1998, 2 distinct research groups, while examining distant supernovae, uncovered evidence indicating that the universe's expansion was not merely ongoing, but was, in fact, accelerating. Galaxies are now receding from each other at an increased velocity compared to their past rates of separation. This finding was so profoundly unexpected, so diametrically opposed to prevailing predictions, that it necessitated the conceptualization of an entirely new cosmic constituent to account for it. That constituent is dark energy, an enigmatic force that pervades the fabric of space, driving everything apart with ever-growing intensity. This groundbreaking discovery garnered a Nobel Prize, and the associated model became the standard framework for understanding the universe. Dark energy was accepted as real, acceleration was deemed a certainty, and the universe's ultimate destiny was envisioned as a cold, solitary dispersal into an infinite void. However, now, in 2025, a new study has cast considerable doubt upon this long-held consensus. By analyzing updated data derived from a multitude of sources, including observations from the Hubble Space Telescope and various terrestrial surveys, a team of cosmologists has proposed that the observed acceleration might not be a genuine phenomenon. While the universe may still be expanding, its expansion could be decelerating, or at the very least, not accelerating with the same vigor as previously believed. If this hypothesis proves accurate, it would dismantle decades of cosmological research, render numerous existing models obsolete, and compel a complete re-evaluation of the nature of dark energy, including the fundamental question of its very existence. How could this discrepancy have arisen? How did cosmologists err in their interpretations for 20 years? The answer lies in the inherent challenges of precisely measuring cosmic expansion. The prevailing methodology relies on the concept of standard candles, celestial objects whose intrinsic luminosity is known. By observing their apparent brightness from Earth, astronomers can deduce their distance. Type Ia supernovae, the explosive demise of white dwarf stars, are prime examples of standard candles, as they all reach a roughly consistent peak brightness. Nevertheless, complexities abound. Supernovae are not perfectly uniform in their properties. Intervening dust clouds can obscure their light, making them appear more distant than they truly are. Furthermore, the calibration of their intrinsic brightness depends on observations of nearby supernovae, introducing further uncertainties. Even minor inaccuracies in any of these factors can cascade into significant errors in the calculated expansion rate of the universe. The recent study re-examined the data employing enhanced techniques, more refined dust correction algorithms, and more sophisticated statistical methodologies. Upon processing the revised figures, the evidence supporting acceleration diminished. It did not vanish entirely, but became less conclusive, more ambiguous. While some models still indicated acceleration, others pointed towards deceleration, and the data lacked the definitive power to differentiate between them. The study's conclusion was cautiously worded, but carried radical implications. We might be uncertain about whether the universe is accelerating or not. Dark energy, the bedrock of contemporary cosmology, could potentially be an artifact of measurement inaccuracies rather than a fundamental physical reality. This proposition remains highly contentious. A significant portion of the cosmological community remains steadfast in their conviction that acceleration is a genuine phenomenon, supported by robust evidence, and contend that the new study's methodology introduces its own set of biases. The debate is poised to persist, fueled by ongoing data acquisition, further observations, and more in-depth analysis. However, the mere fact that this is a subject of active debate, that cosmic acceleration is no longer considered settled scientific fact, is in itself a significant development. What is the connection to 3 Atlas? Once again, the linkage is more thematic than direct. If the large-scale dynamics of the universe, its expansion rate, its ultimate fate, can remain uncertain even after decades of dedicated study, then it should come as no surprise that uncertainties at smaller scales also exist. The universe consistently proves to be less predictable and more enigmatic than we might desire. Whether it pertains to the expansion of space, the decline in star formation, or the behavior of a solitary comet, the underlying pattern remains consistent. Our models are essentially approximations, valuable yet incomplete, and always subject to revision when confronted with superior data. There exists a deeper parallel concerning energy and acceleration. 3 Atlas exhibits non-gravitational acceleration, a deviation in its trajectory that cannot be attributed solely to the force of gravity. The universe, according to the preceding cosmological model, demonstrates accelerating expansion driven by dark energy. Both phenomena involve mysterious forces and challenge our fundamental understanding of how energy and motion operate. While the potential misinterpretation or non-existence of dark energy does not directly impact 3 Atlas, it strongly reinforces the notion that acceleration, whether on a cosmic or cometary scale, is a phenomenon we are still struggling to fully comprehend. The philosophical ramifications are indeed disquieting. We inhabit a universe whose most basic characteristics, its magnitude, its rate of expansion, its composition, its future, are subjects of profound uncertainty. Dark energy, purportedly comprising 70% of the universe's total energy content, remains a profound enigma, its reality and nature unknown. Dark matter, accounting for an additional 25%, is equally mysterious. This leaves a mere 5% composed of ordinary matter, the substance we understand. And even within this small fraction, we encounter objects like 3 Atlas that defy straightforward explanations. Our collective ignorance is vast, our knowledge a mere speck of an island adrift in an ocean of the unknown. Yet, ignorance is not an endpoint, but the very genesis of discovery. Every question resolved invariably gives rise to 10 more. Every solved mystery unlocks doors to deeper, more intricate enigmas. 3 Atlas, the observed decline in star formation, and the uncertain expansion rate are all fertile grounds for learning, for refining our theoretical frameworks, and for extending the boundaries of our comprehension. The cosmos is under no obligation to provide us with simple answers. It is indifferent to the efficacy of our models. It simply exists in all its intricate strangeness. Our role is to observe, to question, to revise, and to persist in our exploration. Thus, the cosmos presents us with surprises on the grandest scales. What then of the smaller scales, at the level of individual objects? This is precisely where the next narrative emerges. Another instance of peculiar chemistry, another celestial body that defies conventional expectations. Does this sound familiar? Part 13. Alien chemistry. Phosphine. Around a brown dwarf. In recent months, astronomers scrutinizing a brown dwarf designated Wolf 1130 AC detected an unexpected presence within its atmosphere, phosphine. This is a relatively simple molecule consisting of a single phosphorus atom bonded to 3 hydrogen atoms. However, its existence in this particular environment presented a significant enigma. On Earth, phosphine is strongly associated with biological processes being produced by microorganisms in environments devoid of oxygen, such as swamps, marshes, and deep-sea hydrothermal vents. When scientists announced the detection of phosphine in Venus's atmosphere several years ago, it ignited a fervent debate regarding the possibility of life existing within the clouds of Venus. That claim has since been challenged, with alternative explanations pointing to geological activity or potential measurement errors. Nevertheless, the allure of phosphine as a potential biosignature persists. Brown dwarfs are essentially failed stars, celestial bodies possessing insufficient mass to initiate sustained hydrogen fusion. They emit a faint glow from residual heat and radiate primarily in the infrared spectrum. These objects are ancient, often billions of years old, and cool down progressively over time. Their atmospheres are complex, containing constituents such as methane, ammonia, water vapor, and various organic molecules. The presence of phosphine, however, was entirely unforeseen. Its formation and stability require specific conditions, and the established chemistry of brown dwarf atmospheres does not readily account for its production. This discovery prompts several critical questions. Is the phosphine biological in origin? Almost certainly not. Brown dwarfs are far too hot and inherently hostile to sustain life as we currently understand it. It is far more probable that its presence is the result of unconventional chemical pathways. These might involve high-energy reactions driven by convective currents that transport material from the interior to the surface, or perhaps photochemical processes occurring in the upper atmosphere. The precise mechanism, however, remains unclear. This represents another instance of peculiar chemistry, a further reminder that the universe generates molecules through processes that we do not yet fully anticipate. How does this relate to 3 Atlas? Both cases serve as examples of chemical anomalies, instances where compositions deviate from established standard models. 3 Atlas exhibits an excess of carbon dioxide and a deficit of water, a ratio suggesting either an unusual formation environment or surface alteration by cosmic rays. The brown dwarf, in turn, harbors phosphine in a location where it is not expected, a molecule whose presence necessitates a specific explanation. Both scenarios compel us to broaden our understanding of what is chemically feasible under diverse conditions. There is also a parallel in how we interpret such anomalies. When phosphine was initially detected on Venus, some scientists swiftly considered the possibility of life. Others, however, urged a more cautious approach, emphasizing the incompleteness of our knowledge regarding Venusian chemistry and advocating that biological explanations should only be considered after all natural processes have been definitively ruled out. A similar dynamic is unfolding with 3 Atlas. Some observe the anomalies and posit technological origins, while others maintain that we have not yet exhausted all plausible natural explanations. The inherent tension between an open-minded receptiveness to radical possibilities and a healthy skepticism toward extraordinary claims is both beneficial and necessary, albeit often frustrating for all involved. The brown dwarf discovery also underscores the profound importance of spectroscopy, the technique of dissecting light into its constituent wavelengths to identify molecular signatures. It was through this method that we detected the phosphine, measured the disproportionate carbon dioxide in 3 Atlas, and continue to study the atmospheres of exoplanets and distant galaxies. Spectroscopy stands as one of astronomy's most potent instruments, enabling us to perform chemical analyses across vast cosmic distances. However, its efficacy is constrained by our understanding of the spectroscopic characteristics of various molecules, their behavior under different environmental conditions, and the potential for other processes to mimic their signatures. Ambiguities are commonplace, and confirmation often requires multiple independent observations. The overarching theme emerging from these discoveries is that the universe exhibits a far greater chemical diversity than we comprehended even a generation ago. Each new celestial object and each novel environment reveals molecules and reactions that were previously unpredicted. This diversity arises from a confluence of factors: the vast range of environmental conditions, from temperatures near absolute zero in interstellar space to millions of degrees within stellar cores. The intricate mixing processes involving cosmic rays, supernova, and stellar winds, all contributing to a dynamic chemical cauldron, and potentially the influence of life itself, introducing its own unique layer of complexity in specific environments. The precise demarcation between natural and biological chemistry in the broader cosmos remains an open question. However, each new discovery incrementally maps this complex landscape. 3 Atlas occupies a position on this map, a data point whose interpretation is still evolving. Its high concentration of carbon dioxide could be a natural occurrence, stemming from its formation conditions or subsequent processing by cosmic rays. Alternatively, it could be something else entirely, though the nature of that alternative remains speculative. The phosphine detected in the brown dwarf is almost certainly natural in origin, a product of atmospheric chemistry that we have yet to fully elucidate. Both instances serve as potent reminders that chemistry is not a simplistic discipline. Molecules form and persist in surprising ways, necessitating constant updates to our models. As our observational instruments advance and our detailed study of celestial objects intensifies, we will inevitably encounter more anomalies, more unexpected molecular signatures, and consequently, more puzzles. This trajectory is inherent to the scientific process. The more we learn, the more we come to appreciate the vastness of our ignorance. 3 Atlas, with its anomalous composition, represents a crucial element in this ongoing educational process, delivering yet another lesson in humility from a universe that steadfastly refuses to be fully comprehended. However, it is not solely chemistry and composition that are yielding surprises. Our perception of the galaxy itself, the very structure and arrangement of our celestial neighborhood, is undergoing a profound transformation. This marks the next segment of our exploration. Part 14, A Sharper Map of the Milky Way. We are witnessing more than ever before. For the majority of human history, the Milky Way remained an enigmatic entity, a luminous river traversing the night sky whose true nature was unknown. Ancient myths attributed it to spilled milk from the gods, while others speculated it was a cloud of incandescent vapor. It wasn't until the 18th century that we grasped its composition of countless individual stars, and not until the 1920s did we understand that our sun was but one among hundreds of billions, all revolving within a vast disk-like spiral structure. Yet, even with this foundational understanding, charting the Milky Way proved an immensely challenging endeavor. We are situated within its expanse, embedded in the disk, and our view is obstructed by pervasive dust and gas. The situation is akin to attempting to map a dense forest while standing in its very center, enveloped by thick fog. In recent years, this scenario has begun to change. Missions such as Gaia, a telescope deployed by the European Space Agency in 2013, have meticulously measured the positions and motions of over 1 billion stars with unparalleled precision. By meticulously tracking stellar movements, astronomers are now capable of reconstructing the Milky Way's intricate structure, identifying its spiral arms, stellar streams, and concealed features. Radio telescopes have augmented these efforts, mapping hydrogen gas distribution and tracing the galaxy's magnetic field lines. Infrared surveys effectively penetrate the obscuring dust clouds, revealing previously invisible star-forming regions. The culmination of these diverse observational efforts is a more precise and detailed map of our galaxy than has ever been achieved. The most recent data, released in 2025, has unveiled structures that were previously unknown or poorly understood. These include newly identified spiral arms, streams of stars gravitationally bound together, presumably remnants of smaller galaxies absorbed by the Milky Way, and pockets of dark matter, inferred from their gravitational influence. These features are now appearing in the observational data like spectral apparitions materializing from the fog. The Milky Way is demonstrably more complex than the simplistic spiral arm model once taught in classrooms. It is irregular, asymmetrical, replete with substructures, streams, and regions of active or recent star formation. One particularly compelling feature is a recently detected stellar stream, a coherent flow of stars moving in unison through space, likely the remnant of a dwarf galaxy consumed by the Milky Way millions of years ago. These streams serve as fossils of past cosmic collisions, providing tangible evidence that our galaxy has not evolved in isolation, but has, throughout its history, incorporated neighboring celestial bodies. Some of these assimilated neighbors may have possessed their own planetary systems, their own comets and asteroids, which are now integrated into our own galactic inventory. 3 Atlas could conceivably be a descendant of such a system, ejected during a galactic collision and having wandered for eons before its trajectory brought it into our vicinity. The enhanced mapping also provides a clearer understanding of the distribution of objects within interstellar space. By analyzing velocities and densities, astronomers can estimate the amount of material drifting between stars, the frequency of collisions or close encounters, and the potential population of rogue planets, comets, and asteroids. These estimates suggest that interstellar space is far from empty. A significant quantity of material populates this vast expanse, much of it dark and invisible, but occasionally an object like 3 Atlas ventures close enough and emits sufficient light to be detected. This observation aligns with the earlier discussion regarding the declining star formation rate. If the Milky Way is aging and the birth rate of new stars is diminishing, then the galactic material is not being incorporated into new systems as rapidly. Instead, it is dispersing, forming a diffuse population of wandering bodies. Over time, these wanderers evolve into the interstellar objects that may eventually visit other star systems. The more accurately we map the galaxy, the better our comprehension of this population becomes, and the more effectively we can predict the frequency with which objects like 3 Atlas are likely to appear. There is also a practical dimension to this improved mapping. As humanity contemplates interstellar exploration, and as initiatives like Breakthrough Starshot aim to dispatch minuscule probes to neighboring star systems at relativistic velocities, understanding the contents of the space between us and our destinations becomes critically important. A collision with even a small particle at 20% of the speed of light would have catastrophic consequences. Mapping the dust, gas, and larger objects along potential trajectories is therefore essential for mission planning. 3 Atlas offers a valuable data point, a sample of what lies beyond, providing insights into expected compositions and potential hazards that require careful consideration. The enhanced map of the Milky Way also possesses significant aesthetic and emotional resonance. It is our home galaxy, the grand cosmic structure of which we are an intrinsic part. Gaining a clearer perspective of it is akin to receiving a more detailed view of one's own residence after having lived there for an entire lifetime. The spiral arms, the stellar streams, and the regions where new stars are being born, all these elements become more tangible, more real. We are not merely detached observers. We are active participants in the ongoing saga of the galaxy, shaped by its history, influenced by its dynamics, and interconnected with all else through the fundamental forces of gravity, chemistry, and the exchange of matter. In this context, 3 Atlas transcends its role as a mere visitor. It acts as a messenger, conveying information from another sector of the galaxy, thereby linking our solar system to the broader cosmic structure. Our study of it not only illuminates the object itself, but also provides insights into the processes that sculpt the entirety of the Milky Way. Each interstellar visitor represents a piece of a larger puzzle, a sample from the vast experimental laboratory of galactic evolution. As our maps become more refined and our instruments more sensitive, we will detect an increasing number of visitors, enabling us to compile statistics and discern emerging patterns. It is conceivable that we might discover that certain types of objects originate from specific directions, thereby indicating particular source regions within the galaxy. We might detect streams of interstellar material akin to rivers of comets and dust flowing through the galactic expanse. It is also possible that we may encounter something entirely anomalous, something that compels us to fundamentally reevaluate what is considered possible. This is the trajectory we are on, a path toward enhanced understanding, yet paradoxically also toward deeper mystery. For every answer uncovered, new questions emerge. The final element in this overarching cosmic context brings us back to Earth, to the future of humanity in space. While we meticulously study visitors from other systems, we are simultaneously preparing to embark on our own journeys, intending to dispatch probes and, eventually, human expeditions beyond our immediate solar neighborhood. This marks the point where the narrative completes its circle. Part 15. From Visitor to Voyager, Humanity's Future in Space. While 3 Atlas has been diligently reminding us that interstellar objects are not only real, but also detectable and profoundly strange, humanity has been quietly preparing for its own eventual role in the grand interstellar narrative. We stand on the precipice of transitioning from passive observers of cosmic visitors to active voyagers ourselves, poised to dispatch probes beyond our solar system, establish vital infrastructure on the Moon and Mars, and develop the advanced technologies that may, at some point in the future, enable us to traverse the vast distances to other stars. The past year has witnessed significant breakthroughs in space robotics and in situ resource utilization, the practice of leveraging materials found in space rather than relying solely on launches from Earth. NASA's Artemis program, dedicated to returning humans to the Moon, has been rigorously testing robotic systems designed to extract water ice from lunar craters, subsequently splitting it into hydrogen and oxygen for propellant, and utilizing lunar regolith for three-dimensional printing of structures. Private enterprises are actively developing sophisticated mining techniques for asteroids, targeting valuable metals and volatiles with potential market values in the trillions of dollars. The overarching vision is to cultivate a space-based economy wherein raw materials are harvested in space, processed in situ, and subsequently employed in the construction of spacecraft, habitats, and essential infrastructure, thereby circumventing the exorbitant costs associated with escaping Earth's gravitational pull. These developments hold profound significance for future interstellar exploration. If we aspire to dispatch probes to distant star systems, and if those probes are to be more than mere microscopic chips propelled by lasers, then we must establish manufacturing capabilities in orbit or on the Moon. The establishment of orbital or lunar-based manufacturing facilities, along with fuel depots, repair stations, and launch platforms, becomes indispensable. The current infrastructure we are developing for lunar and asteroid exploration serves as the bedrock for our future interstellar travel capabilities. Furthermore, advancements in propulsion systems are notable. Ion drives, solar sails, and nuclear thermal rockets are all undergoing testing or are being considered for missions into deep space. While none of these can yet achieve speeds approaching that of light, they represent significant steps in that direction. Our understanding of how different propulsion methods function, the visual characteristics of their exhaust plumes, and the ways in which flight paths are modified all contribute to our ability to interpret observations of celestial bodies like Oumuamua. If we suspect such an object might be utilizing propulsion, knowing how our own technological propulsion appears assists us in identifying unusual signs. This correlation operates in both directions. Examining Oumuamua provides insights into the interstellar environment, potential encounters for our probes, and the composition and dangers posed by objects traversing the vast distances between stars. Should we aspire to dispatch a craft to Alpha Centauri or another neighboring star system, it must be equipped to withstand impacts from cosmic dust, endure radiation, and potentially maneuver around larger fragments. Each interstellar entity we investigate functions as a form of reconnaissance, gathering intelligence about the conditions prevalent in those regions. There is also the possibility, however improbable, that Oumuamua is itself an exploratory craft, meaning we are studying the engineering of another civilization. If this were the case, it would provide an invaluable benchmark, a point of comparison for our own endeavors. How do they construct their technology? What materials do they employ? How do they power their systems? Even if definitive proof of artificial origin remains elusive, the mere speculation compels us to contemplate the design of interstellar probes, their essential features, and the inherent compromises involved. It is a process of engineering by analogy, learning from a hypothetical instance. However, beyond the technological aspects, a more profound question arises: the motivation behind these pursuits, particularly when pressing issues exist on Earth. The answer, at least in part, is that studying objects like Oumuamua serves as a reminder that Earth is an integral component of a much grander cosmic structure. We are not isolated entities. We exist within a galaxy teeming with stars, planets, and the diverse objects that traverse them. Comprehending this context and actively participating in this cosmic exchange is fundamental to what defines a spacefaring civilization. It extends beyond mere acquisition of resources or scientific knowledge, though these are certainly significant. It is about gaining perspective, about recognizing our place as a single thread woven into an immense celestial tapestry. Oumuamua, whether it is a comet, a probe, or something in between, underscores the dynamic and ever-changing nature of the universe. Objects journey between star systems, and matter disperses throughout the galaxy. If matter can spread, and if chemistry and potentially even life can hitch a ride on comets and asteroids, then so too can humanity. The visitors we observe today could foreshadow our own future, a future where human-made probes venture into other star systems, carrying information about Earth, our chemistry, our culture, and our very existence. This future remains hypothetical, still decades or even centuries away. However, the groundwork is being laid now through lunar missions, asteroid surveys, propulsion system testing, and observational campaigns focused on interstellar visitors. Our initial inquiry was what might happen if Oumuamua disintegrated near the Sun, and what implications that would hold for us. The response is multifaceted. Scientifically, it hinges on whether fragmentation occurred, the object's composition, and whether natural phenomena can account for the observed anomalies. Philosophically, it depends on our interpretation of the enigma, whether we perceive it as a natural comet or a deliberate message, a threat or an opportunity. Nevertheless, the overarching answer, encompassing all the parallel narratives we have explored, is that Oumuamua represents a vital stage in humanity's continuous cosmic education. It is teaching us that the universe operates in ways that defy our expectations, that our models require constant refinement, and that each new discovery engenders further questions. It demonstrates that interstellar space is not a void, but an active domain where exchange between star systems is a tangible reality, and that we are intrinsically part of a galactic ecosystem, whether we acknowledge it or not. Furthermore, it highlights the special significance of our current era in cosmic history. We live in a time where we can detect these interstellar travelers, study them, learn from them, and perhaps one day join their ranks. The universe is gradually cooling, star formation is diminishing, and its expansion may be decelerating, accelerating, or behaving in ways yet unknown to us. Chemistry is proving to be more complex than initially believed. Celestial objects are not fitting neatly into our established categories, and the galaxy is far more intricate than our maps suggest. Amidst this profound uncertainty, Oumuamua emerged, strikingly apparent, exceptionally peculiar, and impossible to disregard. It challenged our fundamental assumptions, ignited passionate discussions, and captured the collective imagination. What consequences would arise if it fragmented? We would acquire new knowledge, enhance our theoretical frameworks, and better prepare for future visitors. What consequences would arise if it did not fragment? We would confront even grander questions, contemplate more extraordinary possibilities, and perhaps discover a universe that is more inhabited, more vibrant, and more interconnected than we had dared to envision. In either scenario, the encounter irrevocably alters us. We have witnessed something that tests our understanding, prompting us to think differently, to scrutinize more intensely, and to question with greater depth. Perhaps this represents the true resolution to the initial query. Our fate is not defined by physical peril, asteroid impacts, or fields of debris. It is about perspective. It is about the profound realization that we inhabit a vast, ancient, and mysterious universe, the depths of which we are only beginning to comprehend. Oumuamua, whatever its true nature, is a gift, an opportunity for learning, growth, and for understanding ourselves and our world within a grander context. The observational efforts will persist. December 19th promises to yield enhanced imagery, more extensive data, clearer answers, or perhaps even deeper enigmas. Scientists will engage in debates, scholarly articles will be published, a consensus may materialize, or the existing controversy might intensify. Irrespective of how the technical questions are resolved, the experience of studying Oumuamua has already instigated a transformation within us. It has heightened our awareness of the diverse possibilities, increased our receptiveness to surprise, and fostered a greater sense of humility in the face of cosmic intricacies. We are the species that gazes skyward, that poses questions, that constructs sophisticated instruments for observation and dispatches probes, and that contemplates our existential position within the universe. Oumuamua is an integral part of this narrative, a visitor from beyond our solar system that serves as a potent reminder that our cosmic journey is far from complete. The universe is more astonishing than we ever imagined, and we are in the very process of uncovering just how astonishing it truly is. This is not an end point,